Hello. So today we're going to talk about the finite element solution in 2D. We're going to put the pieces together. If you recall the map that we had for even for the 1D problems, we have the strong form of the problem that we want to solve, and then what we have done in lectures 13 and 14. So this is we already did this, was how to transform from the strong form to the weak form. And then what we did last class was, last two classes has been here, which is we introduced the discretization of functions in 2D and how to calculate gradients in 2D. And what we're gonna do today and the next class, so lectures 17 and 18 are going to be how to put together the strong form and the weak form the weak form together with the discretization of functions in 2D to get a system of equations. And this is very similar to what we did for the 1D problems. I show this map over and over again also for the 1D. It's the same structure in 2D. The things that are a little bit different is the type of discretization that we have, because now we have functions of x and y instead of just functions of x. But the idea is still the same as in the 1D case. So let's get started. So recall the strong form of heat conduction in 2D, and then we're going to talk a little bit about the weak form, then discretization, and then we're going to put that into the weak form to get the stiffness matrix and the force vectors. So the strong form of the heat conduction problem in 2D is find the temperature such that the divergence of the flux plus some source term, which can be a function of x and y, equals 0. And this is on some domain omega, which is a subset of R2, meaning we have some space xy, we have our potato there. So we have to satisfy this PDE in this domain, where the flux is given by the gradient of the temperature minus the gradient of the temperature, remembering that the heat flows from the highest temperature to the lower temperature, and this is sort of the conductivity matrix. And then we have boundary conditions. So we have the natural boundary conditions, q dot n equals some value q bar on the boundary. We're gonna call that gamma q. So this is gamma q, and that's where we know the flux. And then there's another type of boundary condition, which is we know the temperature equals T bar on some other portion of the boundary, which we're gonna call gamma T. And so whatever it is, there's only those two options. Either you have a essential boundary condition or a natural boundary condition. This is the essential boundary condition because we know the temperature, and this is the natural boundary condition because we know the flux at the boundary. So that is the strong form of the problem. We have to find the temperature field. That's our unknown. And then you can see that the temperature field satisfies this second order differential equation. And then this is the natural way in which you find the problem, which we call the strong form. And I'm not going to repeat the calculation of how to go from here to the weak form, so let's just go straight into the weak form. So given this strong form, remember that you multiply by a weight function, integrate, use Green's formula, and then what you end up with is the weak form, which is find the temperature, which is a function of x and y in some space u. And if you recall, let me just put that over here. So u is temperatures that are C0 and that satisfy the essential boundary condition, such that this is the core of the weak form, the gradient of W multiplied by the conductivity matrix times the gradient of the temperature, integrate over the domain, equals the integral of the natural boundary condition and the integral of the source term for all W in the space U0. And then let me just define that here U0 is just functions W that are Z0 such that W equals 0 on gamma t. So whatever has an essential boundary condition, the weighting function disappears at that point. So as I said, this is what we covered in lectures 13 and 14, this going from the strong form to the weak form. And then what we did in the in the lectures 15 and 16 was introducing the discretization with the shape functions in 2D. And so what we said was, and there's a couple of options, so either we have directly the functions in terms of x, y. So for example, we have for a given element, the function over that element is going to be the sum of the shape functions in terms of x, y times the nodal values. And then for the weighting functions, we would have the same. We will have the weighting function as a function of x, y would be, let me just use different index here. So the sum of the shape functions times the nodal values of the weights. And this basically is true for any element and also looks similar to what we had in 1D. So in 1D we had shape functions that were just functions of x. In the 2D case we have shape functions that are functions of x and y. And this could be a triangular element, could be a rectangular element. The only thing that would change is the actual definition of the shape functions, but this is generally true for any element. And that is in the case that you can define the shape functions in terms of x and y. Or there's another alternative, which is, what if I cannot have the shape functions in terms of x and y, but instead I can define the shape functions in terms of the parent domain, which has coordinates xi and eta. So in that case, this looks very similar. So the interpolation of the temperature is the sum of the shape functions times the nodal values. And also for the weighting function is the sum of the shape functions times the nodal values. With the difference that is that you either have the shape functions defined in terms of x and y, or you have them defined in terms of xi and eta. And what you'll see is that in very few cases you can actually define the shape functions in terms of x and y. That's true, for example, for the triangular elements. We were able to define the functions directly in terms of x and y, but most of the time what we will do is we'll have the map between, for example, let me just put here. So for example, this will be useful for if we have a quadrilateral element, then it's easier to map the quadrilateral element from xy coordinates to the psi eta coordinates. And for the functions in terms of xy, actually it's not that many elements. Probably only the triangular element is the one for which we can define the shape functions directly in the xy space, but for pretty much any other element, and even for the triangular elements, we can define the map between the xi eta space and the xy coordinates. So really, this having these functions in terms of x and y is not the common case. The most common case is going to be having a map between the xi eta space and the xy space. But I'm putting both of them here because they are both true. So that's the definition of the interpolation. Let me just change this to J. It doesn't matter, it's just notation, but I want to use different indices for the temperature and for the weighting function. So that's how we define the interpolations in 2D. And then the book actually changes the notation a little bit and introduces matrix notation. Which simplifies the computations, especially if you want to code it. But it's the same thing. So instead of expressing this TE, for example, as the sum of the shape functions times the null values, I'm just going to arrange them in a vector. Where this is a vector that is, the length of this is the number of nodes per element. And obviously the null values is the size of the number of nodes. So you can put this in a vector and just say this times the nodal values. I think the book uses the notation D instead of T, but hopefully you get the point. I think the notation is a little bit secondary. If you put all the nodal values in one vector and you put all the shape functions in another vector, then instead of having this sum, you can just express this as a vector of shape functions times the vector of the nodal values. And that's just going to be a little bit more convenient, especially if you want to code it. So this is true for both the temperature field, but also for the weighting functions. We can just put all the weight function values in a vector and all the shape functions in a vector, and we would have the same. And this is if you have it in the shape functions in terms of xy, but it actually also looks the same if you have for shape functions in terms of xy eta. So in that case, for example, the temperature field in terms of xy eta is going to be, you can just put, again, the shape functions in a vector is exactly the same. The only difference being that here you would need to evaluate the shape functions at xy eta points instead of xy points. But this would look pretty much the same. Just like that. And same for the weighting function. So the weighting functions, just put all the shape functions in a vector and put all the nodal values in a vector. And as I said, the only difference is that you either have the shape functions in terms of xy or you have the shape functions in terms of xy eta. So that's for the interpolation of a function. And then the thing that we covered in last lecture was gradients. So if you just, let me scroll here for a sec, you will need the interpolation of the weighting functions, but you also need the interpolation of the gradients. So then the question is, how do we calculate the gradients? And then here it actually looks a little bit different between the whether you have the shape functions in terms of xy or you have the shape functions in terms of xy eta. So if you have the function directly in terms of xy, so if you have for example, for the temperature, the sum of the shape functions in terms of xy times the nodal values, then in that case, the gradient of the temperature, which is the partial of TE with respect to x and the partial of TE with respect to y, you can get that directly. So here you would get the sum of the partial of shape functions directly with respect to x times the null values, and then here the sum of the partial derivative of the shape functions directly with respect to y times the null values. And you can also change this to matrix notation. So instead of having this, it's convenient to put all the gradients in one matrix. So I'm going to put partial of n1 with respect to x, partial of n1 with respect to y, partial of the second shape function with respect to x, partial of the second shape function with respect to y, and so on, and that times the null values t1e, t2e, and so on. So now this is a matrix that is 2 times the number of nodes, and this is a vector of number of nodes times 1. And this one, if you look at the book, this one is called the B matrix. It has just all these gradients, so that just makes it easier, especially if you want to code it in MATLAB or Python. Then you would have the gradient of TE concisely expressed as this B matrix times the vector with all the null values. And again, this B matrix has the gradients of the shape functions with respect to x and y. And you would get something similar for if you want the gradient of the weighting function, you would get exactly the same. So you put all the gradients in this matrix called the B matrix times the vector with all the nodal values. Now this is true if you have the shape functions directly in terms of x, y. Now what happens if you have the shape functions in terms of psi and eta, which is actually the most likely? So if you have for example TE in terms of psi eta as the sum of the shape functions over the parent domain times the nodal values. So in that case, and this is what I uploaded in the previous video, if you want to get the gradient, you actually have to use the chain rule. So what we have to introduce just before introducing the chain rule is two things. So one thing is the isoparametric map, which is the map between x, y, and psi eta. So that one was x is the sum of the shape functions, which are functions of psi and eta, times the x coordinates of the nodes, and y is sum of the shape functions in terms of psi eta times the nodal values. So this is the isoparametric map relating xy to psi and eta, and then based on that we can get the Jacobian, which is a matrix that is the partial of x with respect to psi, the partial of x with respect to eta, the partial of y with respect to psi, and the partial of y with respect to eta. And that one I defined in the previous video, but this is basically sum of partial with respect to psi times nodal values, sum of partial with respect to eta times the nodal values of the x coordinate, and then the same but for the y coordinate. So this is the Jacobian matrix. And so given these two things, now you can actually calculate the gradient. So if you want the gradient of the temperature when you have the basis functions defined in terms of sine eta, you still want the derivative of Te with respect to x and derivative of Te with respect to y. But now you have to use the chain rule, and essentially what that ends up being is you need the inverse of the Jacobian. So if you can calculate the Jacobian, you can calculate the inverse, and that times what you can do is, I'm gonna skip one step here, but I can go over this if you are curious. I'm just gonna put it already in a matrix, so I'm skipping the sum, otherwise you would have a sum here. So I'm gonna get something that looks like the B matrix. So I have partial of the shape functions, but because the shape functions are in terms of sine eta, I can get derivatives with respect to sine eta. Right, so I get I can calculate directly derivatives of shape functions with respect to psi eta and multiply that by the null values. And in order to get the derivatives with respect to x and y, what I need to have is I need to have this inverse of the Jacobian here at the front. So you can see that this looks very similar to what I had up here, but here, because I had the shape functions directly in terms of x, y, I could just take those derivatives. Here I have the shape functions in terms of sine eta, so I can take derivatives with respect to sine eta, and in order to get derivatives with respect to x and y, then I need to pre-multiply by this inverse of the Jacobian. And you can see that this is a 2 by 2 matrix, this is a 2 by number of nodes per element, this is number of nodes per element times 1. This is actually, when you multiply this 2 by 2 matrix by this 2 by number of nodes per element, then this is again the B matrix. And this is again the Te. So you still have that the gradient of the temperature is going to be the B matrix times the vector with all the nodal values. The difference here is that to get the B matrix, you need to pre-multiply the inverse of the Jacobian times the derivatives of the shape functions with respect to sine eta, because that's what you have. The shape functions are in terms of sine eta, so you can take directly derivatives with respect to sine eta and then pre-multiply by the inverse of the Jacobian to get derivatives with respect to x and y. And the same would be true for the weighting function. So you would have the gradient of the weighting function is the B matrix times the null values. All right, so that brings us to the last point. Let me just scroll again, just to sort of say the whole thing that we're doing is I just did a recap of lectures 13 and 14. I show you the strong form. I show you that you have to do some arrangement and you will get the weak form. I didn't do the derivation here, but hopefully you remember that you have to transform the strong form to the weak form, and it's this integral form. And then on the other hand, you can introduce the shape functions either in terms of x, y, or in terms of psi eta, and you can use that to represent functions and calculate gradients of the functions. And so what we need to do now is to put the discretization into the weak form to get the system of equations. Plug into the weak form. So if you recall the weak form, we have first this integral with the gradient of W times the conductivity matrix times the gradient of the temperature. So if you plug in here that the gradient of the W equals BE times the nodal values, and the gradient of the temperature equals another B matrix times the nodal values. We're gonna put that in here, and then I'm gonna take out the WE and TE because nodal values are not functions of xy or xy eta. So only the shape functions, which are included in the B matrix, are functions of xy or xy eta. So when we put this into the integral and we take out these vectors, what we'll end up with is we're going to end up with a vector of the weight values times, and then here we're going to end up with an integral over the domain of the element, and we're going to get the transpose of the B matrix times the conductivity matrix times the B matrix, integrated over the element times the vector of nodal values for the temperature. So when we put this and this into this first integral, what we end up with is this expression right here. And as you can imagine, this term right here, that is the definition of the stiffness matrix. I'm going to expand that a little bit. Just want to do sort of the whole thing at once, and then I'm going to focus on each one of the different stiffness matrix and force vectors. So here in the second term, you have the weighting function is the WE equals an E transpose times the vector of nodal values. So when we plug that into this term, what we will end up with is we can take the vector of the nodal values of the weighting function, take that out of the integral, and then we end up with the integral over the boundary of the vector of nodal values times the flux. And then this integral right here is going to give us the force vector. And finally, if we have WE equals an E transpose with the W, and we plug that into this integral, then we can again take out the vector of the nodal values, and then what we end up with in the integral is going to be the vector of shape functions times the source term integrated over the domain of the element. I should say this is the part of the boundary corresponding to the element. And so this term right here, this integral right here, is going to give us the force vector of the source term. So this is how we're going to end up with, KE, FEQ, and FES. And we can zoom in a little bit to each one of these terms. As I said, the definition of the stiffness matrix, so once we plug in the discretization into the weak form, we end up with the thing that matters, which is the definition of the stiffness matrix, which, as I said, is going to be an integral over the element of BE transpose times this conductivity matrix times BE. So this is the definition of the stiffness matrix. And you can see from the structure of the B matrices that this is going to give you a matrix that is number of nodes per element times number of nodes per element. If you are a little bit curious about how exactly this matrix looks, you would have to do the integral, and let's just write out what this B matrix looks like. So the B matrix at the end of the day has basically derivatives with respect to x and y. So this will be dn1 dx, dn1 dy, dn2 dx, dn2 dy, and so on. So you can see that this is number of nodes per element times 2, and that times a 2 by 2 matrix which has the conductivity, which if it's isotropic, for example, you will have the identity matrix times a single scalar for the conductivity times the other B matrix, which will be dn1e dx, dn1e dy, dn2 dx, dn2 dy, and so on. And you basically have to integrate this. And for integrals, Gauss Quadrature. Oh, sorry, I forgot to say. This is 2 times number of nodes per element. So if you carry out this multiplication, you will see that you'll end up with this big matrix, which is number of nodes per element times number of nodes per element. And so you could actually write it down. So each of these will be one integral of whatever multiplication you have here. So for example, this will be gradient n1, gradient being just the first row of this, times d times gradient of n1. Then you would have to integrate gradient of n1 times d times gradient of n2, gradient of n1 times d times gradient of n3, for example, and so on. And here you would have gradient of n2 times d times gradient of n2, gradient of n2 times d times gradient of n3, and so on. And this is asymmetric matrix. And this if you want to expand it out. But the easiest way to code it would be to use directly the B matrices, because that's just a little bit more convenient for coding. So that's the stiffness matrix. And then for the force vectors, there's two. There's one which is the vector associated with the flux, and that one we said was the integral over the boundary of the element that is part of the boundary with natural boundary conditions, and then you would just have basically any transpose times the q bar, and this will be a vector which is size number of nodes per element times 1, what will be in every entry. So for example, for the first entry you would get, because this is a vector that is number of nodes per element, and this is just a scalar. So the first integral will be integral of n1 times q bar over the boundary, integral of n2 q bar over the boundary, and so on. And these integrals are over the boundary, so we'll talk a little bit more about those later. But let me jump to the other force vectors. The other force vector is the integral over the domain, and again, shape functions times the source. And so again, this is a vector which is number of nodes per element times 1. This is a scalar. So if you just want to see what this looks like, this will be integral of the first shape function times the source term, integral of the second shape function times the source term, and so on. So you end up with a vector which is number of nodes per element times 1. And how to compute these integrals, either this integral for the stiffness matrix or the integral of the shape functions times the source term, or the integral of the shape functions times the flux. And this is the Gauss quadrature. So which we already talked about. That we can do Gauss quadrature in 2D as well. All right, so assuming you can actually compute the integrals, then you will end up with, you have a definition for the stiffness matrix for an element, you have a definition for the source force vector, and you have a definition for this flux force vector, which is all that you need. So in order to get the global system of equations, then you would have a loop over the elements. For each element, you would compute the stiffness matrix and the force vectors. And then you would do the assembly into the big K matrix and then the big force vectors. Into global stiffness and force vectors. And that assembly is pretty much the same as we did for the 1D, and then you would have this global stiffness matrix times the degrees of freedom equals the different force vectors and the reactions. And once you have this global system, then you can use your usual method of solving this. For example, using matrix partitioning. And that's what I'm gonna do in the next video. So in the next video, what I'm gonna do is I'm gonna solve one example with triangular elements so that it is clear, because this derivation that I've done for this video is pretty much the same for any element, because this, if you had a triangular element, then for example the force vectors would be 3 by 1 because the triangular element has 3 nodes. Well, the linear triangular element has 3 nodes, so you would have 3 by 1 vectors. The stiffness matrix would be a 3 by 3 matrix. But this definition holds for any element. So if you had a quadrilateral element, then this would be a 4 by 4 matrix, and this would be 4 by 1 vectors. So the actual shape of these vectors depends on the element that you have, but in all cases the definition is pretty much the same. So the force vector is the integral of the shape functions times the source term, or the shape functions times the flux, and the stiffness matrix is essentially the integral of the gradients of the shape functions dotted with the gradients of the shape functions, all combinations. So that's it for now. So hopefully this brings together basically the whole picture. You have the strong form of the heat transfer problem. You can set up the weak form. That's one step. Then the other things that we did were we introduced the shape functions in 2D, either in terms of x, y, or in terms of xi eta, and you can do interpolation of the function inside of the element, and you can also calculate gradients. And then in this lecture, if you put these definitions into the weak form, then you end up with the definitions of the element stiffness matrix and the force vectors. And that's what you need in order to set up your global system of equations. You would have a loop over elements. For each element, compute the stiffness matrix and force vectors, do the assembly, just like we have done up to now, and then you'll get this global system of equations, and you will solve it in the same way as we've done in the past, for example, with matrix partitioning. So that's it for